looks like the cosine of theta 1 plus theta 2. Right? And then plus I times, and then here we have the cosine of theta 1 times the sine of theta 2 plus the sine of theta 1 times the cosine of theta 2, and that's beginning to look familiar as well, because that looks like the sine of theta 1 plus theta 2. So we can simplify that, and it looks as follows. This is equal to R1 times R2 times, so this can now be simplified to the cosine of theta 1 plus theta 2 plus I times, and I guess I don't need this parentheses like that. So I times, and this looks like the sine of theta 1 plus theta 2. What then that looks like, if we take a close look at this, if we're going to multiply two complex numbers together in polar form, we multiply the moduli together, and we add the arguments together. So we simply add the angles, so we have theta 1 plus theta 2 for the cosine, theta 1 plus theta 2 for the sine, everything else looks exactly the same, and we'll multiply the moduli together. So therefore, all we have to do is multiply the magnitude, if you want the vectorial magnitude of each of the complex numbers, multiply them together, and then simply add the angles together. And that's how we multiply two complex numbers in polar form. Now, what that tells me is that once you have a complex number in polar form, it's actually rather easy to multiply them together. It looks a lot easier than doing it when it's in standard form of a plus bi. So there's some advantage to using complex numbers in polar form. When we start multiplying, dividing, increasing things to the exponent, you'll see some little rules that makes this quite easy when we put it into a polar form. So that's how it's done. So stay tuned and we'll show you an example of what this looks like with some real numbers. Welcome to MX Online. Now let's take complex numbers that are in the traditional form, a plus bi, and convert them to polar form. And here's two simple examples. We have c equals I plus 1 plus I, and c equals the square root of 2 minus 5i. Remember that to find r, we take the square root of a squared plus b squared, and to find the angle, we take the arctangent of b over a. So here we're going to find r. For the first example, r is equal to the square root of a squared plus b squared, which is 1 squared plus 1 squared, therefore that's equal to the square root of 2. To find the angle, theta is equal to the arctangent of b over a. b would be 1, a is 1, so it would be 1 over 1, which is equal to 45 degrees, which is equal to pi divided by 4. Now we're ready to write this number in polar form. We know the general formula is that c is going to equal to r times the cosine of theta plus pi times the sine of theta. In this case, c can be written as r, which is the square root of 2, times the cosine of pi divided by 4 plus pi times the sine of pi divided by 4. Now we'll do the same for the second example. So again, we need to find r. r is equal to the square root of a squared plus b squared. That would be the square root of 2 squared plus 5 squared. This is equal to 2 plus 25, or the square root of 27, which can be written as 3 times the square root of 3. And then to find the angle, theta is equal to the arctangent of d over a. d is a minus 5, and a is the square root of 2. It doesn't matter that we use a negative in there, because we can have the angle being below the imaginary, below the real axis or above the real axis, so we want to make sure we put in the proper sign. Here we don't care about the sign since we're combining it anyway. Alright, let's see what that's equal to. So we have 5 divided by the square root of 2, we make that negative, and then take the inverse tangent of that, so we get minus 74.2 degrees. Which means that the c cannot be written, because the general format is r times the cosine of theta plus I times the sine of theta. So this can be written as r, which is, where do we go? Right there. 3 times the square root of 3 times the cosine of a minus 74.2 degrees plus I times the sine of negative 74.2 degrees. Oops, and I guess we don't need to put parentheses around that if I want to put parentheses around the angle. Alright, now, we could simplify this a little bit, because the cosine of a negative angle is the same as the cosine of a positive angle. So this could be written as 3 times the square root of 3 times the cosine of a positive 74.2 degree angle. And here we realize that the sine of a negative angle is equal to negative the sine of the positive angle. So this could also be written as minus I times the sine of the positive angle, 74.2 degrees. Notice that gives you really the exact same result. So illustrate, we can write it both ways. And that's how we convert from the normal form c equals I plus bi to a polar form, and that would then be the general form c can be written as r times the cosine of theta plus I times the sine of theta. And that's how it's done. to our lecture online. Now here in this example, we're going to see the power of the technique of virtual work. When we start rotating members of a system, this makes it really easy to calculate the virtual work done. Let me show you why. In a linear sense, to find the work done, we have to multiply via a dot product the force times the small displacement. So this is going to be the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the two. So we can also find the rotational equivalent of work done by taking the torque acting on an object and multiplying it via the dot product with the angular displacement. So when we start rotating things, we have an angular displacement. So you can see that we multiply the torque times the angular displacement via the dot product, or if you want to even call it the moment, times the angular displacement. So here comes the concept of virtual work when we start rotating things. So you can say that virtual work is equal to the sum of all the torques and all the torques acting on the object from I equals 1 to n multiplied, or that's the vector quantity multiplied times the small angular displacement. Or if you like better, you can say that's equal to the sum of all the moments multiplied times the small angular displacement, I equals 1 to n, and if the system is at equilibrium, then we know that that must be equal to 0. And then we can find the reactionary force at the peak with this technique rather than the one we used where we had a linear displacement du in the previous example. So let's go ahead and do that. Let's multiply or add up all the products of the force times the angular displacement and figure out what R sub d is in that particular case. Starting with our reactionary force at A, we can say that the force at A, so reactionary force at A, times the distance, the perpendicular distance from the point of rotation to where the force is acting, which in this case is going to be equal to 0, or this term will tend to 0, so the force times the perpendicular distance from the point of rotation to where the force is acting, times the cosine of the angle between the two. Now notice the reactionary force is up, the theta is up, so that becomes the cosine of 0 degrees. But nevertheless, this term will be equal to 0 because where the force is acting. Now we have the force here, so we have that. The force times the distance from the point of rotation to where the force is acting, that's the perpendicular distance, which is A, times the cosine of the angle between the direction of the force and the direction of the angular displacement, which is 180 degrees. When we add to that, multiplied times the distance, the perpendicular distance from the point of rotation to where the force is acting, which is L, times the cosine of the angle between, so this is acting upward, this is acting upward, they're both pointing in the same direction, so this will be the cosine of 0 degrees. And that of course must equal 0 because the system is at equilibrium. So this is 0, so here we have the cosine of 180 is minus 1, so this becomes minus f times a, plus, here we have the cosine of 0 is 1, the reactionary force at B times L equals 0, or RB times L equals A times F, or the reactionary force at B is equal to A divided by L times F, which of course is the very same result we have in the previous video, but we use a different technique here, and you'll find that this technique is very powerful when we start looking at systems that can bend or rotate or act in different ways. We can even use it on trusses and find the forces on the members of the truss. And this is the technique we use to do that. Welcome to our lecture online. Now let's take a look at the polar form of complex numbers. Again, the geometric representation looks very similar. We have a complex number that has a real part A and an imaginary part equal to bi. And notice we can represent that by considering the distance from the origin to that complex number and call it r. And of course, that's very similar to the modulus. In fact, it is the modulus, but the distance is represented by r. That means that distance from there to there, and by the angle relative to the positive real axis. And when we do that, we can say that A can now be calculated to be r times the cosine of theta, and B can be calculated to be r times the sine of theta. And since C, the complex number, is equal to A plus bi, we can replace A by this and B by this, and then get the new polar representation of the complex number. Let's do that and see what it looks like. C now becomes equal to A, which is r times the cosine of theta plus bi, and B is r times the sine of theta, but now it looks better if we put the I in front. So we're going to put the I in front, so I times r times the sine of theta. Now notice that each of these two terms has an r in it, we can factor it out, so C becomes equal to r times the cosine of theta plus I times the sine of theta. So this becomes the polar representation of that complex number. Now let's investigate the value of r and theta. Now r can be said to be equal to the modulus, which is equal to the square root of a squared plus b squared. So it's basically using Pythagorean theorem to get the value of r. And we can represent the angle theta by saying that tangent of theta is equal to the opposite over the adjacent. The opposite is b, the adjacent is a, so this can be written as b over a. Or we can solve that for theta and say that theta is equal to the inverse tangent of b over a. Now, theta can also be defined as the argument of that complex number. That's probably a name or expression we should become familiar with. So that's the clear representation of a complex number. We can take the number z equals a plus bi, and write as z equals r, the distance from the origin, to the complex number in graphical format, times the cosine of theta plus I times the sine of theta. And again, we write it with the I in front so we don't get confused with calling the angle a complex, the complex part of the angle. We want to therefore put the I in the front so there's no confusion. And that's how it's done. On the particle or on the system. So let's take a simple example. Let's say we have a beam, and let's assume that the mass of the beam can be ignored relative to the force acting on the beam. The length of the beam is L, and its supported have A and a B, so we're going to have two reactionary forces, one at A and one at B. And there's a force applied on the beam, straight down, the distance A away from the left edge of the beam. And the question is, what is the reactionary force at B? Now, of course, we have learned all kinds of methods to find that rather easily. But of course, we're going to show you how to do it using virtual work on this very simple example, so that later on we can do it on much more complicated examples. And you'll see that some of those complicated examples, using the virtual work concept, is actually easier than using some of these other concepts that we have learned before earlier in the course. So, how do we do it using virtual work? Well, we start with the definition that if particles or systems are at equilibrium, that means there is no net force acting on it. That means that the virtual work done is going to be equal to zero. And we can define it as being equal to the sum of all the forces acting on the system. And so that would be the forces, let's call it sum I, from I equals 1 to n. And we're going to dot those forces with du. So we're going to have a dot product between each of the forces acting on the system and multiplying it times the small imaginary displacement du. And we know that's going to be equal to 0. So let's go ahead and do that. Now there are three forces, one here, one there, and one there. And so when we have a dot product, we multiply the magnitude of the force times the displacement times the cosine of the angle between them. So starting with the first force, the reactionary force at A, and let me show you what we're doing here is we're moving the beam an imaginary distance just on the one side where the reactionary force at B is. We're not moving it over here at A, so this force here will not be doing any virtual work, and that part of the beam will not actually be moving, or even it won't be moving in an imaginary sense, so stay stationary. So let's add up all the three dot products. So the first one will be the magnitude of the reactionary force at A times the displacement, so we multiply the times the displacement will be 0, and so we don't have to do anything else there. Then next, we're going to take the force here, so that would be plus the magnitude of the force pushing down, times the displacement. Now, how much did this displace? Well, if at the end of the beam here, the displacement is du, we have to take a fraction of that. The fraction will be A divided by L. So the magnitude of the displacement will be the fraction A over L times du, times the cosine of the angle between the two. Now, the force is acting downward, and d is acting upward. The angle is 180 degrees, which means we're going to multiply this times the cosine of 180 degrees. Then plus, see here, now we have the reactionary force of D, so we have the magnitude of R sub D, times the displacement, again, that's the imaginary displacement, and in this case, it is indeed du, the whole du, times the cosine of the angle between the two, and notice that both pointing in the same direction, the angle is 0, so it will be the cosine of 0 degrees. Now, this part is 0, and of course, all that adds up to 0, because the virtual work done on a particle or a system that is at equilibrium, the virtual work done will always be equal to 0. So this term is 0, then here, the cosine of 180 is minus 1, so this becomes minus f times A over L. Oh, and let's see here, what else can we do? Well, we have a du in each term, so since that's turned equal to 0, the du's cancel, so it doesn't really matter how much we move, or we make the virtual movements, we can cancel out the du, so we have f times A over L, times the cosine of 180, which is minus 1, that's where this minus came from, and then here we have plus R sub D, the reactionary force of D, times the cosine of 0, which is 1, and then that's up to 0. And all we have to do is move this term to the other side, and so therefore the magnitude of the reactionary force of D is equal to A over L times the force applied to the beam. Notice, it's actually quite nice. It works very slick, and notice that even on a simple example, you can see the beauty of the technique. And you say, well, I have much better ways to do that, which is fine. We can use moments or torques or anything like that, but this works for even much more complicated examples, so we'll work our way to the more complicated ones to show you how nice a technique this actually can be. But now you can see how it actually works in a very simple example, and that's how it's done. So welcome to our lecture online. As we hinted in the previous video, there are situations where we can use virtual work when the particle or the thrust, whatever we're considering, is at equilibrium and when the system is not at equilibrium. So in other words, there are two situations where the concept of virtual work can be applied. It's probably most useful when you have a situation where things are at equilibrium. So the first case we're going to consider when the particle is at equilibrium, which means that the net force acting on the particle must be equal to zero, and if there's no net force, then there's no acceleration. So the m times a term in Newton's second law must also equal zero. Which means that if we add up all the forces acting on a particle or acting on a particular point in the thrust, we can assume, or in the system, whatever system we may be looking at, we can assume that if we add up all the forces, they should add up to zero, and therefore we can say that the virtual work done, the delta W, is equal to the sum of all the forces multiplied by a small imaginary distance that we're going to allow the particle or the system to move through. So in other words, if we do a dot product between the imaginary displacement and each of the forces acting on the particle, when we sum them all up, that should equal zero, which means that the virtual work is equal to zero when the particle is at equilibrium. But we can have situations where the particle is not at equilibrium. So the net force is not equal to zero, and therefore there will be an acceleration. F net is equal to the mass of the particle times the acceleration. But now we can also say that the virtual work can also be equal to zero if we look at it this way. The virtual work can now be defined as being equal to delta W, which is equal to the sum of all the forces acting on the particle times the small imaginary virtual distance of displacement, delta U, minus this term, m times a, times the small imaginary displacement as well. Now that makes sense because if the total net force is equal to m times a, and this of course represents the net force, then of course, if I move the ma to the left side of the equation, I end up with F net minus ma is equal to zero. In other words, what's inside the parentheses here must be equal to zero because this is the net force minus the mass times the acceleration of the particle. And then if we take that and multiply that via the dot product times the small imaginary displacement, this then represents virtual work, and this should then also equal zero, because this term will equal zero. In other words, it acts like it's a net force equal to zero. When we subtract from that, that's NA term. Now, what do we call that NA term? That NA term is called the inertial force. So we turn it into a force, we subtract it from the sum of all the other forces acting on the particle, and then the virtual work again can be defined as this times dot delta U, which also will equal zero. So in both cases, the virtual work will equal zero, but when the particle is not at equilibrium, we have to take into account this what we call inertial force portion. And that's how it's done. Welcome to our lecture online. Now let's take a look at a few more rules with conjugates. The third rule tells us that when we take a complex number and raise it to an exponent, and then take the conjugate of that, that should equal the conjugate of that complex number raised to the same exponent. And this rule we're already familiar with, that if we take a complex number and multiply it times its conjugate, we should get the modulo squared. So we'll illustrate that with a few examples. Here we're going to take z equals 2 minus 4i. We're going to let n equals 2. So again, we can do that with any number n, but let n equals 2, which is a little bit easier. And so we take we multiply c by itself. That means c to the second power is going to be equal to 3 minus 4i multiplied times 3 minus 4i. And if we then take this product and take the conjugate of that, that should equal the conjugate of z squared. Let's see if that is the case. So first we're going to multiply these together. This is 3 times 3, which is 9, minus 12i, minus 12i, and that would be plus 16i squared. So this can be simplified to be 9 minus 24i, and since I squared is a negative 1, this becomes a negative 16, and this is therefore equal to 9 minus 16, which is minus 7 minus 24i. And if we now take the conjugate of that, so we take the conjugate of this, which is the conjugate of that, conjugate of this, and this gives us minus 7 plus 24i. So now what we're going to do is we're going to take the conjugate of z and square it, and see if we get the very same result. Alright, so the conjugate of z is equal to 3 plus 4i. So the conjugate of z squared is equal to 3 plus 4i multiplied times 3 plus 4i. This is equal to 9 plus 12i plus 12i plus 16i squared. So this is equal to 9 plus 24i, and this is I squared is negative 1, so negative 1 times 16 is minus 16. So this is minus 7 plus 24i, and notice that, yes indeed, minus 7 plus 24i, minus 7 plus 24i, they're equal to one another. So this has been illustrated with a simple example, not proved.